Hi, today we're going to be talking about if and only if. But before we discuss what that actually means, I'd like you to try this starter. So on the right, we've used four congruent triangles, these ones here. We've made sort of a little cage, and inside we've got a square. Can you use this to prove Pythagoras' theorem? Have a go. Okay, I've purposely given very few clues for this because I just wanted to see. I put this on a problem sheet previously, and it's the same kind of idea. So the first thing we can do is we could label our square on the outside, and we could work out the area of that square in terms of c, and it would be c squared. So that's all well and good. But what about getting it in terms of A and B? Well, we know that this side here is B, and we know that this side here, along here, is A. So if I want to work out the area of the whole square, then I can find the area of the four rectangles, and that's going to be 4 times a half AB. But I then need to also add on this green square, and that's the trickiest bit. But what I've got to realise is that this is also equal to b, and so if the full thing is a and this bit is b, then this little square here is going to be a minus b. And what I'm going to be doing is I'm going to be adding a minus b squared because I've got a square. I then need to figure this out. So this is going to give me 2ab. Then I'm going to expand this bracket. I'm going to get a squared minus 2ab plus b squared. And look what happens. These cancel out and I'm left with a squared plus b squared. Now we've got the area in two different ways. It must be that they are the same, and so we can write down that a squared plus b squared equals c squared. And since we've not really specified exactly what kind of right angle triangle it is, we've just said it's a right angle triangle, then this must stand for all right angle triangles, which is a proof of Pythagoras' theorem. Okay, what we've actually done is the following. We have shown that when a triangle is right angle, it follows that a squared plus b squared equals c squared. This here, we sometimes say it means implies. So a triangle is right angle implies a squared plus b squared equals c squared. Another way of saying that is to say a triangle is right angled only if a squared plus b squared equals c squared. So it's got to be that this is true if this is true. It gets a bit confusing with the language because you could rephrase it as if a triangle is right angled, then a squared plus b squared equals c squared. But my point is that basically this means implies, but it also means only if when you're reading it that way. You can rephrase it, but that's something to take out of this. I prefer to think of it as implies rather than using the words like if and only if. But it is important to have a bit of a feel for it. What we've not done is show the other way around. Okay, and I'm going to talk about that. What is the converse of this statement? Converse actually sort of means the reverse. But it doesn't mean if a triangle is not right angled. The converse is can we try and show that if a squared plus b squared equals c squared, then the triangle is right angled? Can we show the opposite sort of thing? It's not quite the opposite though. That's why we call it the converse. But yeah, what we are interested in is it going this way, and that is all part of Pythagoras' theorem, and something you might not have seen that before. You might have seen proofs of Pythagoras' theorem like I've just done before, showing that if you have a right angle triangle, a squared plus b squared equals c squared. You will have assumed you will have done problems, including in this course, where I've given you a triangle and asked you if it's right angled, and then you've checked for Pythagoras' theorem and seen if it holds or not, and then said, yep, it must be right angled. But that kind of hasn't, that's assuming that basically it goes the other way as well. Okay, now how do we prove this statement? Well, basically, we're going to start with the fact that a squared plus b squared equals c squared. And now we want to prove that this means the triangle is right angled. But there's a stronger statement that we can use that's true for any triangle, and that is the cosine rule. So the cosine rule says that c squared equals a squared plus b squared minus 2ab cos capital C, where we've got capital C here and little c here. That's true for any triangle. But we've just said that a squared plus b squared equals c squared, so I can cancel these out and I get 0 equals minus 2ab cos c. Now, I've got a triangle, so I definitely don't have a equal to 0, I don't have b equal to 0, and I can divide through by this minus 2 as well. I've divided through by all these things, so it must be that cos c is equal to 0, and that has the solution for the smallest angle of 90 degrees. And so what we have done is we've shown that if a squared equals b squared, a squared plus b equals c squared, then a triangle is right angled. Another way of saying it, like so I'm using implies, but the other way. I could also say it as a triangle is right angled if a squared plus b squared equals c squared. That is another way of me going the other way to the left. And you could say it in another way, only if a triangle is right angled, then a squared plus b squared equals c squared. This one's the most confusing. This is the bit I really want you to take out of it, but being aware of the words, again, like I said, is important. One other comment about this is normally, whenever I teach cosine rule for the first time, I actually derive the cosine rule using Pythagoras' theorem, which would be a circular argument. So if I have used Pythagoras' theorem to get the cosine rule, can I really use the cosine rule to prove the converse of Pythagoras' theorem as such? And the answer is no, I really shouldn't do that. But the cosine rule can be derived or proven using other methods that don't require that assumption of Pythagoras' theorem. So this proof definitely still holds. And what I have done then is I have shown that a triangle is right angled, and then I've got both the implied sides. They imply one another now. And what we say is that a triangle is right angled if and only if a squared plus b squared equals c squared. So this is what I mean by if and only if. The if bit means I'm going that way, the only if bit means I'm going that way. So we've proven Pythagoras' theorem and the converse of Pythagoras' theorem. Actually, this whole thing together would be known as Pythagoras' theorem. The fact that they imply one another. It's quite an interesting idea and something that you don't really talk about when you first talk about proofs. You just say that this implies this, but it's really interesting to think, well, does that thing imply it back or not? And it won't always. We're going to do one more where it does, actually. We are going to look at the first, typically the first circle theorem that you see, as I've illustrated on here. For triangle ABC, ABC is inscribed in a circle with AB the diameter if and only if angle ACB equals 90 degrees. We're going to try and prove that this is true. Sometimes in maths you can kind of prove this all in one go as long as like your assumptions are working both ways. But we're not going to talk about that today. I just wanted to sort of say that. We're going to first of all show this way. We're going to say that if we've got a triangle inside a circle with AB the diameter, then the angle is 90 degrees. And this is a proof that you may well have seen before. And what I can do is I can take my triangle I can draw a line going from the center to C, and then I can realize that I've got isosceles triangles here. Actually, isosceles triangles underpin the circle theorems. So I've got this triangle here that I'm sort of outlining, and then this one here. Now, I could label this as A, and I could label this as B. Then, because they're isosceles triangles, this must also be A, and this angle here must also be B. I'm doing all this verbally, but this would be the sort of thing that you would write down for your proof. Okay, I can then add up my angles in my triangle, and I've got an A here, I've got a B here, and then this angle in total is going to be A plus B, and if I add that on as well, that's going to equal 180. So I can then write that as 2A plus 2B is 180, and it follows that A plus B is 90 degrees. I've done it. I've shown it going that way. Okay, what about the other way? How are we going to show that if ACB is 90 degrees, then AB is the diameter. Okay, just bear with me. We're going to start from scratch on this diagram above. Okay, so I can't assume now that I've got these isosceles triangles because I don't know that AB is going through the center. So technically, I need to get rid of that center. It's gone. I can, however, put that 90 degrees in. Okay, let's do this. So I'm now proving it the opposite way. All I know is that I've got a circle around these 3 points. I've got a triangle inside where this is 90 degrees, and I'm trying to show that this is the diameter. By the way, we're kind of assuming here that you can always draw a circle around 3 points, but actually we've demonstrated that earlier that that's possible. So my point here is that sometimes you use previous facts to help you in your proof, and you should sort of state them if they're not completely obvious. All right, so this proof is completely different actually. Let's have a go at it. So something that I can do actually is I could basically draw a line that is parallel to CB, and I could draw a line from here that is parallel to AC, and it will meet back at B. So I know I've got a parallel line here, and I've got a parallel line here. I don't entirely know that it's going to, actually I just realised I don't know that it's going to meet back at B, but I know it's going to meet the line at some point, okay? So yeah, I need to be careful what I'm actually assuming and what I'm knowing. At the moment, I just know that the line will hit. I can't change it, but I know the line will hit somewhere the line CB. Okay, now we can use our knowledge of parallel lines, and one thing we have for parallel lines is if you get this sort of thing, then these two angles add up to 180 degrees. They are co-interior angles. You can prove this by messing about with the circle theorems. If these two are the same, and this plus this is 180, then it must be that this one plus this one's 180. That's just a quick proof of that. So that tells me everything actually, because then I know that this is 90 degrees, okay, because these two must add up to 180. Therefore, this one's 90 degrees because these two must add up to 180 because I've got all these parallel lines, and therefore this is 90 degrees. And what I've shown is it's not just a parallelogram, it's a rectangle, and actually that is enough for me to say I know it's going to hit at B. Okay, I didn't quite know that before, but I do know it now. Okay, it's a rectangle. Right, we're not quite finished, but see how different this proof is. Okay, we're going to finish it off. I know that I can draw, I know that black line basically will go through the center of the rectangle, and I also know that the blue line will go through the center of the rectangle. So this point here is the center of the rectangle. There's one other fact that I can use. I know that I'm not going to prove this one, but basically, when you have the center of the rectangle, it must be that this line is the same as this line. Okay, they're the same length, and also this one is the same as this one, and they're all the same as each other, and that is enough. Basically, I now know that I've got the same distance here is here. This line to the center of the rectangle must be the radius. It's the only thing it could be, and so it must be that AB is the diameter, and I've finished my proof. Okay, so I didn't really write anything down here. I sort of just explained it all because there might be quite a lot of words. I think the main thing I want you to take away from this is that we have shown that it's true either way, and we can therefore use this if and only if relationship. Okay, so far we've proven Pythagoras' theorem, but we've proven that it's actually an if and only if relationship. Okay, so we can write the implies arrows both ways, and then we've even looked at the this circle theorem and shown that this implies this and this implies this. Is it always true that one statement implies another statement and the other statement implies it back? And the answer to that is no, which is what makes this such an important topic, really. We're not, if it was always true, we wouldn't really care about discussing it. We'd just maybe prove it one way and be like, hey, it's all sorted. But it's not always true. So the first example we're going to look at where it's not always true is as follows. X equals 3 implies x squared equals 9. Well, that's sort of true by definition. Squaring just means timesing it by itself, and so that's going to be correct. However, if x squared equals 9, does that imply that x equals 3? And the answer is no, because there's another solution when you take the square root, which is x equals minus 3. So yeah, it's only a little technical thing, but it does not, it means it does not follow from it. And so this is a strictly one-way relationship, basically. A statement that implies another statement, but it doesn't imply it back. That's going to be true with other statements involving, like when you get two solutions to an equation. The solutions, there might be more than one solution, so you can't just ignore that. And a slightly less trivial example is this challenge question I set previously. So I asked you for square numbers greater than 0 to prove that p, an odd prime number, implies p can be written as the difference of two squares in only one way. Actually, that's quite an involved proof, which I'm not going to talk about now, but it is true. However, does it follow that p can be written as a difference of two squares in only one way implies p is an odd prime number? And for that, we can maybe look in an example. So if I've got 9, I know I can write it as a difference of two squares. So I can write it as a plus b, a minus b. And what I'm trying to show is that I'm trying to show that if, okay, I'll show you where I'm going with this. So basically, if I can write 9 as the difference of two squares, which I know I can, because actually I can write any odd number as a difference of two squares, then if I look at this, then either this is going to be 9, and this is going to be 1, and that's going to mean that a plus b equals 9, and a minus b equals 1. I can add these together to give me 2a equals 10, a equals 5, and then b is going to equal 4. I've solved a simultaneous equation. Another way around this could have been would be 3 and 3, however, and then I'd get a plus b equals 3, a minus b equals 3, and that's going to give me 2a equals 6, a equals 3, and b is going to have to equal 0. So I've got one solution, which 9 is equal to 5 squared minus 4 squared. That's what I've just shown. And then I've got a second solution that 9 is 3 squared minus 0 squared. But I said if a square number is greater than 0, so actually this one doesn't count. And basically what I have shown is that 9 can only be written as a difference of two squares in only one way. But that does not imply that 9 is an odd prime number, because I know that 9 is equal to 3 times 3. So sorry, I hope I haven't got too technical here, but this is like a less trivial example, say, than this one here, where it follows from this that this is true, but it doesn't follow the other way around. Okay, it might be true for some of them, but it doesn't always follow, because 9 is a counter example.